Greetings everyone, I'm Luigi Starace. I'm a researcher at the Università di Studi Napoli Federico II. I'm involved in the FAIR project and more in detail in the activities of Spoke 3, which focuses on resilient AI. In this poster presentation, I'll give an overview of the research activities we are carrying out within Spoke 3 in the context of simulation-based testing for AI-intensive advanced driver assistance systems, or ADAS for short. ADAS are systems designed to enhance vehicle safety and automate certain driving tasks, like lane keeping, adaptive cruise control, or emergency braking. As these systems become more and more AI-driven and take on increasingly complex decision-making tasks, ensuring their safety and reliability is critical. Failures in these systems can have very serious consequences, making their resilience a key concern. However, testing these AI-intensive ADAS in the real world poses significant challenges. On-field testing is time-consuming and thus very costly, gives rise to potential safety hazards, somebody might get hurt, and cannot capture the full range of possible scenarios that the system might encounter when employed in relatively unpredictable real-world environments. This is where simulation-based testing comes into play. The simulation-based testing approach leverages advanced simulation engines capable of producing photorealistic 3D renderings and detailed physics simulation, providing a high-fidelity virtual environment for testing. By simulating a wide variety of driving scenarios using these tools, it is possible to test ADAS in a controlled, repeatable, and more efficient way. But even in simulation, exhaustively testing all possible scenarios a vehicle may find itself in isn't feasible. There are simply too many variables at play. Therefore, we need strategies that allow us to generate the most effective test scenarios, focusing on edge cases or high-risk situations where the ADAS might actually fail. One of the strategies we are working on leverages reinforcement learning. Reinforcement learning is a machine learning approach where an agent learns to make decisions by interacting with its environment. Instead of being explicitly programmed, the agent receives feedback from its actions in the form of rewards or penalties, which guide its behavior over time. Through this process, the agent becomes increasingly skilled at achieving a particular goal, which in our case is creating challenging scenarios for testing ADAS. Indeed, our goal is to train an autonomous agent that can modify existing test scenarios to make them increasingly challenging for the ADAS. At the beginning, the agent starts by making random changes to a scenario. This could be something like tightening a turn in the road, adjusting the speed of nearby vehicles, or altering environmental conditions such as the weather or visibility. Initially, these changes may not necessarily result in a difficult scenario for the ADAS, but through trial and error and after many iterations, the agent learns which modifications lead to system failures or near failures. The agent is continuously evaluated based on how effectively its generated scenarios expose weaknesses in the ADAS. With each iteration, the agent refines its approach, gradually focusing on the specific types of scenarios that are most likely to challenge the ADAS. In more detail, we start from an initial set of predefined scenarios, and the agent progressively adjusts different parameters, learning over time which variations and which combinations of parameters are the most effective. Each iteration with the environment provides the agent with valuable feedback. If a modification leads to an ADAS failure, near failure, or in some way triggers a dangerous behavior, the agent receives a positive reward. Conversely, if the ADAS performs well, the agent receives a lower reward or a penalty, encouraging it to explore more difficult test scenarios. We are currently evaluating our technique by applying it on a real-world automated lane-keeping ADAS. Early results are promising, and we have uncovered a number of different faults in that system. Future research will focus on investigating more sophisticated representation strategies for test scenarios, including the possibly model-based ones, and into incorporating more domain knowledge into the test scenario generation process. Moreover, testing the approach on different ADAS subjects as well as using different simulation platforms is a necessary step to investigate the generalizability of our approach. This concludes my poster presentation. Thank you very much for your attention. And if you want to discuss these topics further, drop me an email at luigi@starace@tunina.it.